We're going to look at switching between binary and hexadecimal. And we'll start out with doing binary to hex. But let's talk about the hexadecimal system. And I'm trying a different stylus this time. Hopefully my writing won't slant clear to the left like it did when I was trying to use that computer screen. So we'll see what happens here. But we talked before about base 10 being based on the numbers 0 through 9. Okay, and we did binary, which is base 2, which was based on the numbers 0 through 1. You can see for both of these systems, if our base was 10, we go up to the digit 9. Our base was 2, we go up to the digit 1. And that's true of any number system. If I was doing base 8, my digits would be 0 through 7. So we're going to be working with base 16. So what digits am I going to use? I can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But what happens when I get to 10? Okay, so the rule of a digit is it can only take one spot. So I can't use a 1, 0. So we start using letters of the alphabet. So 10 becomes A, 11 becomes B, 12 becomes C. That's not what I meant. Let's see if I can. I don't remember how to erase. I'll have to come down here and get my eraser tool. Know what happened to my thought process there? Okay, so we run out of numeric digits from our traditional numbering system, so we start using letters. So A is 10, 11, 12, 13, 14, and F is 15. Okay, so those are the values 0 through 15 for our base 16 numbering system. Okay, so that can get a little bit confusing for people. So let's start out with an example. And before I do, I am going to create a little table to help us with our conversions, because I want to point something out here. You've seen 16 pop up when we've been doing binary. When we do the place values, we had a 16 right here, right? This was 2 to what power? It was 2 to the 4th power, right? And 8 was 2 to the 3rd, 4 was 2 to the 2nd. That's how we did our place values. Okay. What are our place values going to be in base 16? We're going to have a place that has a 16 to the 0 power. That's the ones place, because anything to the 0 power is 1. We'll have a 16 to the 1st. That'll be our 16s place. Okay. A 16 squared, which is 256. And a 16 cubed, which is, oh, my mind just went blank. I think it's 4096. Okay. Really, most of the time, we're going to be working with the first two places here. Okay, so we'll do 2-digit hexadecimal numbers. So you'll see numbers in hex that look like something like F7 or 3E. Those are numbers we see. Sometimes we'll use longer ones, and you'll see really, really long hex numbers in some places, but we won't be converting them by hand. For hand conversions, we'll try to stick to 2 digits. Okay, but our place values work the same way. How many 256s do we have in 1,000? Well, we have 3, and we have a remainder left over, right? And then we have to figure out how much of that gets taken up. That's if we're doing decimal. We'll talk about that later. We're going to start with binary to hex. Okay, so let me clear my canvas, and I will show you the easy way, because hexadecimal and binary conversions are really easy. And it's based on this idea that these 4 digits add up to 16. actually 16 combinations, 0 through 15, right? 2 to the 4th power. So this idea of 4 digits in binary becomes the same as 1 digit in hex. Okay, so we'll see this in just a second. So let me clear my canvas. So I always tell people the easiest way to start when you're doing binary to hex is to make the chart. Okay, just like we did when we did binary to decimal, we said make that little chart 1, 2, 4, 8, 16, 32. We're going to do the same thing for hex, and we're going to do the numbers 0 through 15. So I'm going to write down 0, 1, 2, 3, 4, 5, 6, 7. Let's go ahead, because I'm not sure how to use my stylus really well yet. Let's do 0 in binary. Oops. Got carried away there. Oh, no, I didn't. It's all zeros, right? What's a 1? Well, that would be a 0 in the 8s, a 0 in the 4s, a 0 in the 2s, and a 1 in the 1 spot. What's a 2? 0, 0, 1, 0. A 3 is 0, 0, 1, 1. Now, a pattern starts to emerge here that should help you in making this chart. And, excuse me. You may be seeing it already. Maybe you're not. Okay. But if you look over here, 0, 1, 0, 1, from each number, especially it's easy to see going from even to odd, 0, 1, 0, 1, 0, 1, 0, 1 on this right column. And my columns aren't really good as, because like I said, I'm using a tablet and I'm not really good at the tablets yet. What about the second column in? What's the pattern here among those numbers? Okay. 0, 0, 1, 1, 0, 0. What do you think it's going to be down here? Okay. And then let's look at if I can get this to switch. Let's look at the second column. These numbers right here. What's the pattern there? 0, 0, 0, 1, 1. So this alternates every other number. This one alternates every 2 numbers. This column alternates every 4 numbers. And we'll see the last column when we get to it will alternate every 8 columns. Okay. So let me finish this out. 0, 1, 1, 0, 0, 1, 1. So there's my numbers 0 through 7. Let me, if I can, figure out how to move my canvas over here a little bit. There, that gives me a little bit more room. All right, let's continue here. We'll have 8, 9, 10. Oh, we can't use 10. We have to use the letter A, B, C, D, E, and F, even though we know this is 10, 11, 12, 13, 14, 15. So let's do the same conversion chart over here that we had. I know that the first column is going to go 0, 1, 0, 1, 0, 1, 0, 1. And the second column will alternate every 2. Oops, excuse me. It will alternate every 2, but it starts with zeros. And I left the 1 off this column earlier. And then the third column goes every 4. Goes 0, 0, 0, 0, 1, 1, 1, 1. And this column was all zeros for the first 8 digits, and it's going to be all 1s for these digits. So there are my hexadecimal to binary number conversions from 0 to 15. Okay. But you can see you don't have to have them memorized, and I didn't really spend any time converting them. I could say this B is the same as 11, right? So 8, 4, 2, 1, right? There's an 8 plus a 2 plus a 1. That's 11. So I could have done all the conversions manually, but it's a whole lot easier to use these patterns to do it. Alternate by 2s, alternate by 4s, alternate by 8s. And I quickly have a way to convert at least the first 15 numbers, 16 if we include 0, 0 through 15. I have a way to convert that pretty easy. So let's pretend somebody gives us the binary number. Oh, and I don't want to use that pen. Let's go back. Let's use red. Somebody gives us the binary number 6F. How do I convert it to binary? Well, I pointed out that 4 digits of decimal, or 4 digits of binary, was equal to 1 digit of hexadecimal. And we can actually use this principle to convert 2-digit hex numbers into binary numbers, or 3-digit hex numbers, or 4-digit hex numbers, but it's all based on these groups of 4. All right, so 6 is 0, 0. Excuse me, it's not. Spoke without thinking. 0, 1, 1, 0. That's a 6. And I know an F is 4 1s. We just converted this number in hex to its binary equivalent. It's that easy. If you can do this little chart first. Okay? If you have this little chart memorized, which it's really not that hard to memorize. I know 3 1s is a 7. I can do most of these. I always remember A is 10 and it's 10, 10. B is 1 more than that and it has an 11 at the end. Okay. So it's not too hard to make this chart, whether you do it by pattern, rote conversion, whatever you want to do. But if you can make this chart from scratch, the conversions are easy. Let me see if I can. That's not what I wanted to do. I thought there was a thing I could do with my pen here. Aha, there it is. I'm starting to like this little tablet that I'm using. All right, so let's do another one. C7. No, I already did 7. Let's do C. Let's do the number CA. Okay. So C is 1100 and A is 1011. That's it. So sometimes we put a little 2 down here, like a subscript to tell people this is hexadecimal. Sometimes with hexadecimal numbers, you'll see 0x and then the actual number come afterward. The X basically tells people this is hex. Okay. Or sometimes you'll see A with an H after it to tell people it's hex. Okay. Or sometimes it's explicitly stated or obvious from the problem. Here's the ones that aren't obvious. It's when you see 7-2. Is that 72 in base 10? So that's a good place. If we put the H after it, everybody knows it's hex. Or 110. Is that 110 in base 10? Or is it 110 in base 2? Okay. So make sure, if the context isn't perfectly clear, make sure you use some kind of notation to let people know, hey, this is a hex number, not a base 10 number. Okay. It's obvious when there's a letter in it. Most people will assume it's hex. Let's go the other way. Let's make a binary number. 1011000. 0, 1, 1. Okay, let's convert this number from binary to hex. And to do it, all we got to do is divide it into groups of 4, working from the right to the left. Okay, so normally we're going to see a whole byte, so 8 digits. So it wouldn't matter if we go from the right to the left. But what if somebody, if the leading two were zeros and somebody left it off only 6 digits? So we got to make sure we go from the right to the left as we set up our groups of 4. But once we do, 0, 0, 1, 1 is right here. That's a 3. And 1, 0, 1, 1, I know that's an 11, which is a B. And if I didn't know it by heart, I could come over here and look at it. Okay. So I just converted that binary number to hex. Let's do one more. And I'm going to, those two little red dots are bothering me. And this tool is kind of fun to use. Why isn't it getting rid of that one? There we go. All right. I'm sorry for the distraction there. I'm having too much fun with my little tool here. 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1. Okay. What's that binary number in hex? Divided into groups of 4. 1, 0, 0, 1 is 9. 1, 0, 1, 1 is 11, which is B. Okay. 1, 1, 1, 0 is E. So this number is EB9. So hex and binary conversions are very, very simple. As long as you can do this.